Everything that has ever existed, every star, every ocean, every sandwich you have ever eaten, every argument you have ever had, every love letter ever written, every dinosaur that ever walked, every black hole spinning at the edge of the observable universe. And every single atom in your body came from something smaller than the period at the end of this sentence. Not metaphorically, literally, measurably. And here's the part they never tell you in school. Before that moment, there was no space, there was no time, there was not even a void sitting there waiting. The word before did not apply to anything, because time itself had not been invented yet. The universe did not begin inside something. The universe began, and existence just showed up along with it. I want you to hold that for a second, because I have been thinking about this for weeks, and it still makes my brain fold in half. 13.8 billion years ago, everything that would ever exist was compressed into a single point of infinite density and infinite temperature. Physicists call it a singularity. I call it the most insane starting condition for anything, ever. And then for reasons that even our best equations cannot fully explain it, expanded. Not slowly, not gradually. In the first fraction of a second, the universe grew from something smaller than an atom to something larger than a solar system. It did not explode into space. It was the explosion of space. Every point in the universe was rushing away from every other point simultaneously. And from that single unthinkable moment, everything that you see when you look up at the night sky was born. This is the Big Bang. And I am going to explain it to you like you are 5 years old. Not because it is simple, it is the furthest thing from simple, but because the story of how we figured this out is one of the most astonishing detective stories in the history of human thought. And buried inside that story is a twist that I genuinely did not see coming the first time I encountered it. I will get to that. But first, I need you to understand just how wrong everyone was, for a very long time, about the most basic question a person can ask. Where did all of this come from? For most of human history, the answer to that question was either a god or a variety of gods, or some kind of eternal steady state in which the universe had simply always existed and always would. The universe was the furniture of reality. It did not have an origin. It was just there, the way a mountain is just there. Nobody asks the mountain when it started. You just walk around it and accept it. Then along came a Belgian Catholic priest named Georges Lemaitre, and he had the audacity to do the math. In 1927, Lemaitre published a paper suggesting that the universe was not static, it was expanding. He derived this from Einstein's equations of general relativity, the same equations Einstein himself had fiddled with to prevent them from suggesting exactly that conclusion. Einstein added what he called a cosmological constant, a kind of mathematical fudge factor to keep his model of the universe from expanding or contracting. He wanted a stable, eternal universe. He wanted the furniture to stay still. Lemaitre looked at the equations without the fudge, ran them forward, and then did something even more radical. He ran them backward. If the universe is expanding now, he reasoned, then at some point in the past it must have been smaller. And if you keep going backward in time, tracing that expansion in reverse, you eventually arrive at a single starting point, a moment of beginning. Lemaitre called it the hypothesis of the primeval atom, a single, extraordinarily dense, extraordinarily hot point from which everything emerged. Einstein's reaction when he first heard this idea was essentially to tell Lemaitre that his math was fine, but his physics was atrocious, which, coming from Einstein, must have felt like being complimented on your shoes while being told you have no soul. Einstein came around eventually, but we will get there. Here's something I want you to notice before we go any further. Lemaitre was a priest, a man of faith. And he was the one doing the calculation that said the universe had a beginning, a moment of creation. You might expect religious institutions to love this. You might also expect secular scientists to be comfortable with the alternative, an eternal, uncreated universe. But the opposite was actually true, and that tension is going to matter later in this story. In the 1930s and 40s, the idea of an expanding universe was gaining traction. Edwin Hubble, working at the Mount Wilson Observatory in California, had already confirmed by 1929 that distant galaxies were moving away from us. The farther a galaxy was, the faster it was receding. This was consistent with expansion. The universe was getting bigger, which meant it had been smaller, which meant Lemaitre might be right. But might be right is not the same as proven. And here's where our subplot enters the picture, because while some scientists were cautiously warming up to the idea of a cosmic beginning, one of the most brilliant and combative astrophysicists of the 20th century was doing everything in his power to kill it. His name was Fred Hoyle, British, sharp. Funny in the way that very smart people who are also slightly insufferable tend to be funny. Hoyle championed what he called the steady-state model of the universe, the idea that the universe had no beginning, that it had always existed, and that as it expanded, new matter was continuously created to fill the gaps, keeping the density constant. Eternal universe. No messy singularity, no moment of creation, clean, elegant, and as it turns out, completely wrong. In 1949, Hoyle was giving a radio interview on the BBC and decided to take a shot at Lemaitre's theory of the primeval atom. He called it, mockingly, this Big Bang idea. He said it as a dismissal. He was trying to make it sound ridiculous. And instead, accidentally, he gave the theory the name that stuck forever. Fred Hoyle, the most vocal opponent of the Big Bang, is the reason we call it the Big Bang. I love that so much. But here's the thing about Hoyle. He was not wrong because he was stupid. He was wrong because reality is stranger than even brilliant people are comfortable with. And for a while, neither side had the definitive proof they needed. What would it even look like to prove that everything began from a single hot point 13.8 billion years ago? What kind of evidence could you possibly find for something that happened before stars existed, before planets existed, before atoms had fully formed? The answer arrived in 1964. And it arrived in the most gloriously accidental way in the history of science. Arno Penzias and Robert Wilson were not trying to prove the Big Bang. They were not even particularly interested in cosmology at the time. They were engineers working at Bell Labs in New Jersey, and they were trying to build a better radio antenna. Very practical people, very specific goal. They had this massive horn-shaped antenna, and they kept picking up a persistent background noise that they could not get rid of. It was coming from every direction equally. It did not matter where they pointed the antenna. The noise was there. It was uniform. It was constant. It was annoying. They checked everything. They recalibrated the equipment. They checked again. They even found that pigeons had been nesting inside the antenna. And this is my favorite detail in all of physics history. They carefully cleaned out what they professionally described as white dielectric material. Pigeon droppings. They cleaned pigeon droppings out of one of the most important scientific instruments in history, pointed the antenna at the sky, and the noise was still there. What Penzias and Wilson had accidentally found, while scraping bird excrement out of a radio horn in New Jersey, was the cosmic microwave background radiation, the afterglow of the Big Bang itself. When the universe was about 380,000 years old, it cooled enough for atoms to form, and the energy that had been trapped in the dense plasma of the early universe was suddenly released in a flash of light that has been traveling in every direction ever since. That flash, stretched and cooled by 13.8 billion years of cosmic expansion, is now a faint microwave hiss that fills the entire universe uniformly. It is everywhere. It is always there. You cannot escape it. Your microwave oven operates at frequencies close to it. When old analog televisions displayed static between channels, a small percentage of that visual snow was actually the cosmic microwave background. Literally, the echo of the first light in the universe showing up on your television set. Penzias and Wilson had found the fingerprint of the beginning of time. They won the Nobel Prize in Physics in 1978. The pigeons did not. Fred Hoyle never fully accepted it. He kept working on modifications of the steady-state model until the end of his life. Sometimes being brilliant means you are also really committed to being wrong. But here is where I need to slow down, because we have been talking about evidence and discovery, and I have not actually explained the thing itself yet. What actually happened at the Big Bang? What does it mean for everything to come from a singularity? And this is the part where I have to be honest with you. This is where even the physicists start sweating a little. Let me use a metaphor and then immediately tell you why the metaphor is wrong, which is actually how all good science communication should work. Imagine you have a balloon, a small, deflated balloon. On the surface of that balloon, there are a bunch of dots drawn with a marker. When you blow up the balloon, those dots move away from each other. Not because they are moving along the surface, they are not moving at all relative to the surface, but because the surface itself is expanding. Every dot sees every other dot moving away from it. And the farther away a dot is, the faster it appears to recede because there is more surface between them stretching simultaneously. That is more or less how the expansion of the universe works. Galaxies are not flying through space away from each other like shrapnel from an explosion. Space itself is expanding between them. The galaxies are relatively stationary. It is the medium they sit in that is growing. Now, here is where the metaphor breaks down. A balloon has a center. The Big Bang did not happen at a center. There is no special point in the universe where it all started. No place you could point to and say, there, that is where existence began. Every point in the universe was the starting point simultaneously. This is very hard to visualize because we are three-dimensional creatures trying to think about four-dimensional space-time. And our brains were really designed for the savannah, not for quantum cosmology. I am not going to apologize for your brain's limitations. Mine has the same problem. The first fraction of a second after the Big Bang is where things get genuinely extraordinary. And I mean fraction in the most extreme sense imaginable. In the first 10 to the power of negative 43 seconds, a unit of time so small it does not have an everyday name, though physicists call it Planck time, all four fundamental forces of nature were unified into one. Gravity, electromagnetism, and the two nuclear forces were a single force. The temperature was 10 to the power of 32 degrees Celsius. At this scale, our best theory of gravity, general relativity, breaks down entirely. Quantum mechanics, our best theory of the very small, also struggles here. These are the two most successful scientific theories ever constructed, each verified to extraordinary precision in their respective domains, and right at the very beginning of the universe, they contradict each other. Neither one alone can describe what happened in that first sliver of time. This is not a scandal. This is an open invitation. The search for a theory of quantum gravity, a framework that reconciles these two great pillars of physics, is one of the central quests of modern science. String theory, loop quantum gravity, and several other approaches are attempting to answer this. None of them have succeeded completely yet, which means that the very first moment of the universe remains, in the most technical and rigorous sense, a mystery. Not a spiritual mystery, a mathematical mystery. We know the equations break down, we just do not know what replaces them. But we do know what happened after. A few fractions of a second in, the universe had cooled enough for quarks to form the fundamental building blocks of matter, quarks bound together into protons and neutrons. The universe at this point was still unimaginably hot and dense, a seething plasma of particles and radiation. Matter and antimatter were being created and destroyed in equal proportions. And here is one of the strangest facts in the entire story. For every billion antimatter particles created, there were 1 billion and 1 matter particles. That tiny 1 in a billion asymmetry is why you exist. Matter and antimatter annihilated each other almost completely, but that minuscule surplus of matter, 1 extra particle per billion, survived. Everything you see, every star, every planet, every person. We are all the remainder from a near-perfect cancellation. We are the fraction that was left over. I find that either deeply humbling or deeply hilarious, depending on my mood. About 3 minutes into the universe's existence, protons and neutrons began combining to form the nuclei of the lightest elements, hydrogen mostly, some helium, roughly 25% of all the matter in the universe, trace amounts of lithium. This process is called Big Bang nucleosynthesis, and the predicted ratios of hydrogen to helium to lithium match with extraordinary precision what we actually observe in the oldest, most pristine regions of the universe today. That match is one of the strongest pieces of evidence we have that the model is correct. Then the universe did something that sounds boring, but is absolutely fundamental. It waited. For about 380,000 years, The universe was too hot for atoms to form. Electrons moved too fast to be captured by nuclei. The universe was opaque light, could not travel more than a short distance before being absorbed or scattered. Then, as I mentioned, the temperature dropped enough for electrons to settle into orbit around nuclei. Atoms formed, the universe became transparent. Light, for the first time, could travel freely across vast distances. And that moment, the moment the universe became see-through, is what Penzias and Wilson detected in New Jersey, while scraping pigeon droppings off their antenna. After that, for about 200 million years, nothing visible happened. This period is called the Cosmic Dark Ages. No stars, no galaxies, just hydrogen and helium gas, slowly being pulled together by gravity, clumping and condensing and heating up, until the first protostars ignited and the universe lit up for the first time. Population. 3 stars, astronomers call them. Enormous, brilliant, burning fast and hot, forging the first heavy elements in their cores, carbon, oxygen, nitrogen, iron, and then exploding as supernovae, seeding the universe with everything heavier than hydrogen and helium. We are made of that material. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all of it was forged in the hearts of stars that exploded billions of years before the Earth existed. Carl Sagan said, "We are made of star stuff," and he was being entirely literal. Now here is the part I promised you, the part I said I would save, the part that, when I first understood it properly, made me sit very still for about 3 minutes. We have been talking about the Big Bang as though it is a settled, complete theory, and in many ways it is. The evidence is overwhelming. The cosmic microwave background, the abundance of light elements, the large-scale structure of the universe, the redshift of distant galaxies, every major prediction of the Big Bang model has been confirmed. But there is a question that the Big Bang itself cannot answer. A question that sits just before everything we know. A question that is technically outside the reach of science as currently practiced and may always be. What caused the Big Bang? Or, more precisely, what was the singularity? What existed before it? Can the word before even apply to a time before time existed? For decades, the default scientific answer was essentially to refuse the question. The laws of physics break down at the singularity. There is no before. The question has no meaning. This was a philosophically convenient answer because it stopped the regression. You did not have to explain what came before the Big Bang because there was no before. Time began with the universe. But in the 1980s, physicists Alan Guth and Andre Linde proposed a modification to the Big Bang model called cosmic inflation. And inflation changed everything about how we think about the beginning. Inflation proposes that in an extraordinarily brief period, from about 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe underwent an exponential expansion of almost inconceivable speed. In a time span far shorter than any natural human concept can hold, the universe grew by a factor of at least 10 to the power of 26. Some models suggest far more. A region of space smaller than a proton expanded to the size of a grapefruit in a fraction of a moment. This sounds insane, and it is, and it was not proposed because physicists wanted to sound dramatic. It was proposed because it solved 3 separate, serious problems with a standard Big Bang model all at once. The first problem was the flatness problem. The universe appears to be geometrically flat. Parallel lines do not converge or diverge across cosmic distances. For this to be true at the precision we observe, the initial conditions of the Big Bang would have to have been fine-tuned to an extraordinary degree. Inflation provides a natural explanation. Any initial curvature would have been flattened out during the expansion, the same way the surface of a balloon looks flat when you blow it up large enough. The second problem was the horizon problem. 2 opposite ends of the observable universe are about 93 billion light years apart. They have never been in contact with each other. Light traveling at the speed of light simply has not had enough time to make the trip in 13.8 billion years. And yet the cosmic microwave background temperature is the same in every direction to an accuracy of 1 part in 100,000. How can 2 regions that have never interacted be the same temperature? Inflation solves this by proposing that before the exponential expansion, these regions were in contact. They equilibrated. Then inflation drove them apart faster than light could follow. The third problem was the magnetic monopole problem, which is a bit technical, and also the least cinematic of the three. So I will just tell you that inflation solves it and move on. Here is the genuinely strange part. Inflation was not invented to solve the philosophical problem of what came before the Big Bang, but it opens the door to answers that are stranger than the question. Some versions of inflation theory, particularly Andre Linde's eternal inflation model, suggest that inflation never truly stopped. It stopped in our local region of space-time, giving rise to our observable universe. But in other regions, inflation continued. And in those regions, quantum fluctuations could have triggered new inflationary bubbles, each one becoming its own universe with its own physical laws, its own constants, its own structure. An infinite, self-reproducing multiverse in which our universe is one bubble among an unthinkably vast number of bubbles, each causally disconnected from all the others. This is not science fiction. This is a serious proposal, taken seriously by some of the most rigorous physicists alive. It is also currently untestable, which is the part that makes other serious physicists deeply uncomfortable. A theory that cannot be tested is not quite science in the traditional sense. It is something else. What that something else is, mathematics, metaphysics, inspired speculation, is a live debate. And here is where I want to bring you back to Georges Lemaitre, the priest, the man who first did the calculation. When Lemaitre proposed the primeval atom in the 1920s, Pope Pius XII was delighted. He announced publicly that Lemaitre's theory was proof of the Christian doctrine of creation. The universe had a beginning. God made it. Science confirmed religion. Lemaitre was reportedly horrified. He wrote to the Vatican asking them to stop using his physics to make theological arguments. Not because he was not religious, he was deeply so, but because he believed science and religion operated in entirely separate domains. Science describes the how, religion addresses the why. Conflating them, he argued, was bad for both. He was right, and his instinct was prophetic, because the question of what came before the Big Bang, the question that looks like it should be answered by God or by physics or by both, turns out to be a question that resists clean answers from any direction. The more carefully you look at the beginning, the stranger it gets. The quantum vacuum that physicists describe as the ground state of space-time is not nothing. It seethes with virtual particles, fluctuating energy, probabilistic potential. Some models suggest the universe could have originated from a quantum fluctuation in such a vacuum, spontaneous creation from a quantum nothing. But then the question is, what generated the quantum vacuum? And the regression continues. Stephen Hawking and James Hartle proposed a model in the 1980s in which the universe has no boundary in imaginary time, a concept that requires accepting that time itself behaves differently at the Planck scale, taking on a spatial character rather than a temporal one. In this model, asking what happened before the Big Bang is like asking what is south of the South Pole. The question assumes a geography that does not exist. There is no before the beginning. Not because we are forbidden from asking, but because the concept dissolves under the mathematics. I am going to be honest with you. I do not think this is settled. I do not think any living physicist thinks it is fully settled. The honest position, the position that I find most compelling, is that we are genuinely at the edge of what human cognition and human mathematics have so far managed to reach. Not because the answers are unknowable in principle, but because the tools we have, built the equations, the experiments, the instruments, were built by creatures that evolved on a medium-sized planet around an ordinary star. And we are trying to use those tools to describe the moment before space-time itself existed. The surprise is not that we have gaps. The surprise is how far we got. 13.8 billion years of cosmic history. And we can trace it back to the first fractions of a second with confidence. We can describe the formation of every element lighter than iron. We can map the large-scale structure of the universe with surveys containing hundreds of millions of galaxies. We can detect gravitational waves from black hole mergers a billion light years away. We can read the temperature variations in the afterglow of the Big Bang to 1 part in 100,000 and use them to reconstruct what the early universe looked like in 3 dimensions. We are not the leftover, insignificant species on a forgettable rock orbiting an average star. We are the part of the universe that figured out where it came from. That is not nothing. That is the most extraordinary thing I know. And there is one more piece I have been holding back, because it is the piece that, for me, makes all of this feel personal rather than abstract. The atoms in your body are old. Your hydrogen atoms, and you are mostly hydrogen because you are mostly water, are among the oldest material objects in the universe. They formed in the first 3 minutes. They have been part of stars, part of interstellar clouds, part of planets, part of oceans, part of single-celled organisms, part of dinosaurs, part of the soil, part of ancient humans you will never know the names of. They are on loan to you for the duration of your life, and when you are gone, they will go somewhere else and be part of something else. The atoms do not care. They are incredibly well-traveled and entirely indifferent. But here is the thing. The carbon in your brain, the carbon that is right now processing these words, forming connections, building understanding, that carbon was forged inside a star that exploded billions of years before the Earth formed. That carbon crossed the galaxy inside a supernova shockwave, got swept up into the nebula that eventually became our solar system, settled into the Earth, got cycled through the biosphere for billions of years, got absorbed into food, got metabolized into you, and is now being used to think about the explosion that originally created all the raw materials for stars. The universe began. It expanded. It cooled. It made atoms. Those atoms made stars. Those stars made everything heavier. Those stars exploded and made planets. On one planet, the atoms organized themselves into life. That life evolved brains. Those brains asked where they came from. And the answer, traced all the way back, is a single moment 13.8 billion years ago, smaller than the period at the end of this sentence. Fred Hoyle, for all his stubbornness, actually made one of the greatest contributions to this story. In 1952, he predicted that carbon must have a specific energy resonance state, called a resonance, in order for stars to produce carbon in the quantities we observe in the universe. He did not base this on direct calculation. He based it on the fact that carbon-based life existed. We are here, therefore the physics must allow for abundant carbon, therefore the resonance must exist. It was later confirmed in the laboratory. It was called the Hoyle state. The man who tried hardest to deny the Big Bang inadvertently provided one of the most striking pieces of evidence that the universe is constructed in a way that permits the existence of beings who can ask about its origin. Make of that what you will. I started by telling you that everything that exists came from something smaller than a period. I told you that before that moment, there was no space, no time, no before for anything to mean, and I told you that the universe began and existence showed up along with it. What I did not tell you at the start, what I want to leave you with now, is that the universe did not just produce matter and energy and galaxies. It produced curiosity. It produced the capacity to look backward across 13.8 billion years and reconstruct what happened before there were eyes to see it. A Belgian priest ran the equations backward and found the beginning. 2 engineers cleaning pigeon droppings off an antenna detected its echo. A physicist who spent his career trying to prove it never happened accidentally gave it the name by which everyone now knows it. The Big Bang was not just the beginning of the universe. It was the beginning of the story that eventually asks itself where it came from. Georges Lemaitre died in 1966. Just weeks after learning about the discovery of the cosmic microwave background, the evidence that confirmed the theory he had built 40 years earlier from Einstein's equations and his own extraordinary intuition, he had spent 4 decades being called wrong, being called naive, being told that science had no room for a beginning. He died knowing he was right. He died knowing that the universe had a first moment and that he was the one who found it. The period at the end of a sentence is not nothing. It is everything.